Hi, my name is Çetinkaya-Rundel. I am a professor at Duke University and a developer educator at Posit. And today I'll be talking to you about visualizing data. If you'd like to see the slides, they are at this address on the first slide, mine.corto.pub/visualizing data. All right, let's start by talking about why visualize. Here's a quote from Tukey. The simple graph has brought more information to the data analyst's mind than any other device. Another way of saying a picture is worth 1,000 words. So we might want to visualize data to discover patterns that may not be obvious from numerical summaries. Let's take a look at a few examples. Here we have 13 data sets, each with 142 observations. So each row here represents a data set. And for each observation, for each data set, for each observation, we have two variables, an X and a Y. And what we've done in this summary table is for each of these 13 data sets, we have calculated the average X and the average Y value. And if you sort of quickly glance up and down the slide, you'll see that these are exactly the same. Same number of observations, same average for X's, and same average for Y's. Let's add some more summary statistics. Same standard deviations for X and same standard deviations for Y. These are looking awfully like the exact same data set. And one more, we have the correlation between X and Y for each of these as well. So the summary statistics are exactly the same. So how, if at all, are these 13 data sets different from each other? Numerical summaries won't tell you that. A picture, on the other hand, might. So here we have plots of Y versus X in each of these facets, 13 facets for 13 different data sets. And we can see that on the first one, things are shaped like a dino. The second data set looks like a random scatter. Maybe data set 6 is showing some stars and ellipse. Sort of 2, it's almost like X is a categorical variable, like a binary, and Y has some random values in data set 13. So these data sets are awfully different from each other, but their summary statistics are the same. So without visualizing, there's no way we would have uncovered this. We might also visualize data to convey information in a way that is otherwise difficult or impossible to convey. Let's take a look at some of these visualizations we've grown very accustomed to and maybe slowly starting to forget about, but we've grown very accustomed to that at the earlier end of COVID-19. Here we have death rates that have for various countries, and we're comparing them to historical averages. So the top of the plot, the title says, the death rates have climbed far above historical averages in many countries that have faced COVID-19 outbreaks. And this is data from August 2021, so over about a year ago. It would be a lot of words to describe what's happening here. So with this visualization, you can, allow your audience to sort of maybe focus on a facet they might be interested in, but then have the opportunity to compare that to the other countries if they want to do so. Here's another example. This is a percentage of residents age 12 plus that are fully vaccinated as of, again, August 27. This is from the New York Times, August 27, 2021. So the numbers have probably changed over the year, but we can see here that there's a lot of information embedded in this map, right? This heat map, or a choropleth map, as we would call it. It would be very difficult to describe this in words. Providing it in a visualization form, particularly providing it in an interactive visualization form, where actually on the New York Times webpage, if you go to the source link at the bottom, you can click and see how the distribution changes across the ages, is a really nice affordance that you wouldn't be able to do without the visualization. And here's a final example, also about from a year ago. This is by Kieran Healy. Kieran is a professor of sociology at Duke University, and he does lots of data visualization. And this was his visualization for all-cause mortality in the United States, comparing the year 2020 to 2015 through 2019. And each of the sort of rows in this visualization represent a state, except one of them is United States overall, that's been bolded. And the hollow circles are years 2015 to 2019, and the red triangles are in 2020. So we can see, for example, New York City, which has been sort of set aside also from the rest of New York State too, has a lot, the mortality rate is a lot higher than compared to sort of what we were seeing in the other years. So again, a lot of information being presented in a single graph that allows the reader to focus on the bits that they might be interested in. Here's North Carolina, for example. That's how things went in North Carolina in 2020. And this would be a lot to describe in words alone, or even given a summary table. So now that we've talked a little bit about why visualize, why not visual, and why visualize, let's talk about how to visualize and how not to visualize. The first case study we're going to look at is on trends for instructional staff, employees in universities. So this is a report from about a decade ago at this point, trends in instructional staff employment status, looking at data from 1975 to 2011. We don't have data on every single year between those. So we have about 10 or so data points here. And this plot is a screen grab from a report that has been published by the American Association of University Professors, which is a nonprofit membership association of faculty and other academic professionals. So if we were to ask what trends are apparent in the visualization here, we can sort of see different types of faculty sort of grouped together on the x-axis. So we have, for example, full-time tenured faculty, tenure track, full-time non-tenure track, part-time, and graduate student employees. And we can see also that the different colored bars represent the years. And for example, for part-time faculty, the percentage of total instructional staff, it has been increasing over the year. And we can see that for full-time tenure track faculty, the percentage has been decreasing. But let's ask ourselves, is the best way to represent these data? So whenever I'm critical of a visualization, I like to take a look at the raw data. So in this on this slide, we can see that each row is a type of faculty, and each column represents a year for which we have data. And in the cells, we have the percentage of instructional employees in that category. So 29% in 1975 were full-time tenured faculty. That number fell to 16.7% in 2011, for example. Here is a recreation of that same visualization. I haven't tried to match the colors, but what I've done, I make these plots using R and the ggplot2 package in R. So if you are also somebody who does make visualizations, as opposed to sort of just interpret them or work with others who make them, you might be interested in sort of how these were created. And if you go to the slides, you can see at the very end, I linked to the GitHub repository where the code for generating these visualizations are included as well. So you are welcome to dig into the code if you would like, but otherwise sort of sit back and enjoy the presentation of how we can take this, the SAD plot, and make it better. The first thing we might want to do is, first of all, representing percentages as parts of a whole. So if we sort of think of each of these buckets as a whole, we can take a look to see how it will be a little bit easier to see how the percentages have changed over time. It is hard to compare the widths of these bars to each other, though. So another thing we might want to do, because this is clearly time series data, we're looking at something happening over time, we can actually put the year on the x-axis and the percentages on the y-axis and take a look to see how the percentages have been changing. Now that story about part-time faculty increasing seems a lot more clear. But there's something wrong with this plot. If you take a look at the x-axis, you can see that the different years, 1975 to 89 to 93 to 95, seem equidistant from each other, but those years are not equally distant from each other. What happened here is that we had some data where the year was stored as a character, and so when we sort of naively made this visualization, this was plotted as a categorical variable, and it is not. So if we actually convert to numeric, and now we have actually the correct number of, like the correct amount of distance between the various points where we have data collected, we can actually see that the story of full-time tenured faculty versus the full-time versus the part-time faculty is even a lot more clear, how the drop-off has happened versus how the increase has happened. Another thing we can do is to use an accessible color scale. So this is the default ggplot2 color scale. I think it looks, pretty like rainbow colors, but that same visualization, if for someone who has deuteranopia, so a type of red-green confusion, looks just like this. And we can see that it's really hard to tell the difference between the graduate student employees and part-time faculty here. And similarly, that same visualization looks like this for folks with protanopia, a type of red-green confusion. So I usually sort of start mocking up my plots using whatever default colors there are, but then I want to make sure that I am using an accessible color scale. So this is the Okabe-Ito color scale that is known to be accessible, and I can sort of apply that to my visualization. And finally, instead of having folks do color matching, because even if you are using an accessible color scale, it can still be hard for folks to see. And also, it takes a little bit of sort of staring at the plot to understand what's happening. The orange, for example, is on top here on my legend, but it's the fourth item here, sort of going down the lines on my plot. So my eye has to sort of go back and forth to see those. So instead, I can actually use direct labeling, where I'm labeling the lines with the type of faculty without the need for your audience to have to read a legend. And furthermore, you might actually use color to draw attention. So previously we talked about using an accessible color scale, but what about actually using color to tell your story? Our story here was that the percentage of part-time faculty who are doing instruction have been increasing, and we're not really interested sort of in the rest of the breakdown necessarily between the other types of faculty. So if that is the story you want to tell, then we can sort of use the same muted, I use gray here, color for the rest of the faculty, and then highlight the part-time faculty in red so we can draw attention to that. I could go one step further and say maybe we don't even need to label the other types of faculty. Maybe we still want to leave them sort of at separate lines. But if we're really not interested in that breakdown, we can simply show the part-time faculty and then label everything else other faculty. And finally, we might use labels to further communicate the message. So if we go to the previous slide, our title was Trends in Instructional Staff Employment Status 1975 to 2011. Instead, we might say instruction by part-time faculty status on a steady increase as our title, and then use the sort of the information about where the data is coming from. Those are the national totals, for example, and the years in the subtitle of our plot. And finally, we might simplify things. So if you sort of miss that, going from this visualization to here, I don't really need all those grid lines. They're there by default, but I don't really need them to tell my story. So sort of just like in fashion, before you leave the house, you want to think about is there one more thing I can take off? So I've removed the grid lines here to make this a more clear presentation. So in summary, we want to represent percentages as parts of a whole. We want to place variables representing time on the x-axis when possible. We want to pay attention to data types. So we want to represent time on a continuous scale, not years as levels of a categorical variable. We want to prefer direct labeling over legends, use accessible colors, but also sometimes use color to draw attention. And finally, pick a purpose and label, color, and annotate for that purpose. We want to make sure that, everything sort of we're putting on the plot is helping us tell the story we want to tell, the message we want to send. We don't want our audience to be looking for the message we want them to get. And communicate your main message directly in the plot labels. And finally, simplify before you call it done. So before you leave the house, look in the mirror and take one thing off. Let's move on to the second case study. Here we're going to look at data on bachelor's degrees. So in this case, each row in this data set represents a field/year combination. For each combination, we know the number and the percentage of graduates, and only the most popular 3 fields are identified. The remaining fields are sort of lumped into another. So we have a bunch of years, the field, and then the percentages given in the table. Here is that same data as a table on top and as a visualization at the bottom. We can see the raw data on top. There's a lot of numbers there, but maybe somebody needs that data. And we can see sort of the trends for the various fields over time in the bottom using a line plot like the one we made previously. So when do we choose to do a table versus when do we choose to do a plot? Tables are good for looking up or comparing individual values, to display precise values, to include detail and summary values, and to display quantitative values, including more than one unit of measure. And plots are useful to reveal relationship among whole sets of values. So this idea of seeing trends increasing or decreasing tend to be a lot harder with a table, and to display a message that's contained in the shape of the values of patterns, trends, and exceptions. So do I have to choose between these two? Maybe I don't. Maybe if I have an audience that's interested both in the exact values, but also in seeing the trend, I can use something like this. These are called spark lines in the trend column. So you can basically embed sort of a visualization inside of your table. Technically, they're a little bit more tedious to make, of course, but depending on sort of the software you use to make this, there may be a nifty option for doing that. But the message I want to send here is that oftentimes we think about, should it be a table or should it be a plot? And you might ask yourself, why not both? So in summary, a table may be preferable to a visualization if your audience needs the precise values. But a table can be enhanced with a visualization so that we can actually show the trends as well. And our last case study is on COVID-19 deaths. So a bit of a grim topic, but something that we've unfortunately been very accustomed to hearing about. So here we have data where each row represents a country and date combination. For each combination, we have the total number of cases, the cumulative cases, so up to that point, and the days elapsed since the 10th confirmed COVID-19 case in that country. So for example, in China, in January 22, 2020, there were a total of 17 cases, and that was the first day where at least 10 cases had been confirmed. And then you can see on the next day, we had one more case, and that's basically case number. So we increment the cumulative cases by 1 for that. So here's a plot of those data for a set of countries. We have US, Brazil, UK, France, Turkey, and China. And these are data as of this Sunday, November 13, 2022. So we're looking at sort of how the number of deaths have increased in a linear scale. So you can see, for example, on the y-axis, we have the number of deaths from COVID on a linear scale. And what that means is that countries where the population is much bigger are going to look, the lines for them are going to look a lot higher as well, simply because there are more people in those countries. So we have sort of a right skewed distribution of the number of deaths because of the larger populations in some of these countries compared to others. And then in some cases, there may be sort of, the reporting might be different as well. Over here, we have the cumulative number of deaths, but on a logged scale. And what this allows us to do is to sort of start thinking about the rate of change from one date to another. At the sort of towards the beginning of the pandemic, there were many sort of news outlets that would show either the data on a linear scale or a logged scale. And there was lots of discussion around which is the right thing to do. Is a logged scale the right thing to do, knowing that the public may not be familiar with logged scales? Or is a linear scale the right thing to do, even though it is not really telling us a whole lot about the rate of change? So you might ask yourself, which plot do you prefer? But also think about why. thinking about who is your audience. Can you explain what log scale means, what its benefits are, and are they able to consume that information? How much are you going to need to annotate your plot in order to be able to say it? If we actually look at the first 25 days, which plot you prefer might potentially change. We can actually see on the logged scale the differences between the rates of change a lot better. So over here, for the countries that we're plotting versus in the linear scale where everything looks almost like overlapping with each other. So in terms of talking about the early rate of change, the logged scale might indeed be preferable. So in summary, your data scale matters. And keep in mind, not just best practices, but also your audience and the amount of supplementary information you can provide. Oftentimes, going just with best practices alone may not be sufficient if your audience is not necessarily prepared to consume the visualization you're providing them. So that's sort of the end of the story with the three case studies. I hope that you've enjoyed sort of this walkthrough of how to visualize and how not to visualize. So let me leave you with a few resources. There are some books that I am particularly fond of for learning about how to make visualizations. Some of them actually also dip into the software details of doing so, and some of them do not. The first one, Data Visualization, A Practical Introduction by Kieran Healy. If you are going to be making your visualizations with R and ggplot2, is a fantastic way to get started. But also has lots and lots of discussion around sort of, how to make the right visualization for a particular type of data and how to think about your audience. Another really nice book is Fundamentals of Data Visualization by Klaus Wilke, who actually works on the ggplot2 package, but this particular book does not have the code in it. It's really about sort of the fundamentals, and it's a really nice read. How Charts Lie by Alberto Cairo, Presenting Data Effectively by Stephanie Evergreen, and Data Vision by David McCandless are also really nice books for sort of introducing you to a vast, variety of visualizations, and also teaching you how to think about which visualization to choose for which situation. There's a Data Visualization Society community that you might want to be a part of, and there are also lots of tools for doing those. So all of the visualizations presented here in my presentation are created with R and ggplot2. And as I said, if you are someone who does actually use R, and are interested in seeing the code, if you click on this link here, it will take you to the GitHub repository where you will find the Corto file, a technical system for sort of authoring technical documents with which I've made this visualization, and the code is actually embedded in the slide deck that you'll be able to find. So you can, if you like, take that code, recreate this entire slide deck, and work through the code as well. Thank you very much, and I hope you enjoyed the presentation.